Okay, tips one, thanks for coming. I just anticipate my talk is not so easy to understand because there are several new procedures at the same time, and then maybe I need your collaboration for everything. Okay, we work in a large group in Frascati Laboratory mainly. The motivation was to explore in a deeply way the role of flux to produce a normal seed. The point is, before we begin just using electrons, but it was not enough, and we add ions. To move ions to get flux, you need quite large voltage. In this experiment, we work up to a counter electrode of 1,200 volts, sinusoidal. To study the effect of only the voltage to stimulate flux, we make a step down about the previous experiment. In the previous experiment, we used geometry to promote non-equilibrium condition. Now we remove any thermal discontinuity, and we just focused on voltage effect. So at that time we developed nodes, cappuccino nodes, and so on. So now the system is locally as homogeneous as possible. We identify only one parameter. The main is we want to understand the effect. So oversimplification is the only possibility. During the MID conference, 6 months before, we explored the effect of electrons. So it means Richardson law, well known to people, and the Child-Langmuir law about the movement of electrons. Later, we realized it was not enough to have our wishing, so we explore the Pascal regime that Pascal developed about 130 years before, Germany, to study the insulation properties, high voltage insulation. So experiment made at room temperatures and DC condition. This experiment gives us a lot of quite important information, how to manage the system to avoid that the excess heat vanish over time. Moreover, at the end, we just study again the strange effect of spontaneous voltage, a current coming out from insulated wire put inside the reactor. And it was tested also from Mattia Valate, Bob Greiner some years before. The starting point of the effect of all, I think, anomalous heat generation seems quite easy. Just load as much as possible some proper material, palladium, titanium, nickel, or alloy. We used alloy. And after, try to move it. Moreover, we observed, not only us, that some flux of electrons can help the effect. The main drawback, at least in our experiments, from long time, that at the beginning, when you make some changing, you have a normal heat. Later, almost always, all excess heat going to zero. So it means the equilibrium condition is zero power equilibrium. You have to move, you have to make non-equilibrium. And so the problem is we want something useful. We need continuous excitation. We need flux or something more, or damaging of material, something difficult to identify in some way. But the point is, if we have low loading to get working Richardson and Pascal regime, you need high temperature and low pressure. But we have both. It means you deload the wire. So it seems no solution problem. And this is the main reason, because we concentrated at the Pascal regime, because it allows to have some residual pressure, not really zero, very close to zero, like in the Richardson law, and you can work with some residual gas. We need the deuterium inside. And moreover, if we alternate between negative and positive voltage, we have also the electrons during the positive shape of the wave. We have a structure like a old diode, anode and cathode, with some residual gas inside the tube, the vacuum tube. Not really vacuum, some residual gas. Okay. This is the quite famous Pascal law. So this is the product between pressure and distance, anode cathode. Is the voltage necessary to have conduction. So reducing pressure constant, the voltage is lower, and that's start again. So this minimum is the operating point. Means if we have larger voltage, we can work at a larger pressure. Quite simple. This data was made in DC condition at room temperature. They make some other studies at low temperature and high temperature. Usually at high temperature we have some advantage. Before we concentrate about use nodes, because the nodes don't need energy to have non-equilibrium, but they have some limits. So now we just forgot for the moment nodes and go over. We just use the same constant because it's a peculiarity to aggregate dissociation of hydrogen deuterium from molecular to atomic state. Very, very easy. It's the best material for this purpose. And moreover, the hydrogen deuterium is stored inside the constant itself. So it's like local, every million of reactor where you can make the reactions. At a point, we observed that as the wire is thinner, as the results are better. So a simple explanation is just geometry. If you have, because the thickness of sponge almost constant, 10, 20 micron, the ratio between the bulk, very low activity, and the surface increase, reducing the wire diameter. Quite simple explanation. To make a sponge, before you use the very high pulse, up to 10-20,000 ampere per square centimeter, repeated several hundred times. But now use more simple just for check. Anyway, using the pulse is the best way, even time consuming. And moreover, the wire is covered from specific materials like iron that helps for the reaction, strontium because it's a low working emission material, and potassium and manganese. Potassium is cofactor, and manganese reduce the evaporation of potassium. And moreover, it is a multi-layer approach, so several layers of 10, 100 nanometers each other. Other points, we need atomic hydrogen source locally, and we use the glassy, some glassy as the peculiarity to absorb atomic hydrogen and not molecular. It was found from Langmuir in 1928. So, other point is a thermodynamic emission, Richardson law. This is the well-known Richardson formula, and it depends upon working function of the material. We selected low working function material, and this is a graph how the current at the surface of the cathode change changing the temperature or the work function. So the changing is really giant. The people that first developed a low working function material was Iwamura in 1986, more or less, but at a low temperature. Now, very, very fast about the Capuchin geometry. The Capuchin node has the peculiarity to have local thermal gradients without adding energy, but the main limitation is the number of nodes you can make and easy to break. Here is the local temperature. It's a true photo. So you have 300-400 degree difference in a few millimeters distance. As some aspects is really ideal, but some limitation. Later we make a more sophisticated way to increase the number of nodes of turning, and we have to put some insulating layer, and we develop a new kind of glassy sheet made of two materials in the same sheet altogether, thanks to collaboration of CG company, France, Italy, and the Italian company that help us from 8 years, but some budget and several technical suggestions. So it was a practical advantage for everybody. Okay, so I try to. This is the sketch of the reactor. We have 3 reactors on each tube, always constant, so we can compare the data, changing just the core, the kind of core, but the geometry always the same. Here's a sketch of the super Capuchin node geometry, quite complicated, sophisticated, but now we forget for the moment. The energy balance is made by airflow calorimetry, very, very simple. Input, output in the same 8, just crossing to increase turbulent air. Very, very simple, nothing special really. Here is a sketch photo of the reactor before mounting the 3 wires, the 3 cores. The tail of the reactor inside the insulating box before closing. And moreover, to have homogeneity in respect to the calibration, we put aluminum foil thick blacknet to have more homogeneous temperature. Now, the new one, this is the new geometry, is a sort of several coaxial geometry. It's really not easy to understand. So just give key points. After you can read in your, from the presentation. It's a sort of coaxial. The inner is a counter electrode made of iron, insulating a sheet, active wires put inside the insulating sheet, constant wire inside, or platinum, and over insulating, thermal insulation, and reflecting for infrared. So in this way, we can have a large temperature up to 800 and 900 degrees with enough low power. Here these are schematic of some auxiliary circuitry because we use very large voltage and several times we have damage of the electronics. Here's a sketch about the 3 wires, all the same. Platinum, constant 200 microns, constant 350 microns. This is the auxiliary circuit to measure resistance ratio of the wires and the protection network, several protection network. And this is the simple oscillator we built to have sinusoidal wave up to 600 volts, just using the main, and we measure the current flowing at the counter electrode through this resistor, voltage and the current. Some typical result. This is what happens to the counter electrode when the pulse, even present, is not absorbed from active wire. So you have almost the same voltage in and out of the resistance. No effect. So you give power, nothing happens. This is an intermediate regime. So the temperature is high to have a Richardson effect, but the pressure was too low. We intentionally reduced as much as possible the pressure. So we have symmetric current, and the Richardson law means electrons and ions, quite similar. There is some effect, but it was weak. The third one is the best regime, and it really more okay. This is the regime that gives the most advantage. In this measurement, we have the largest chassis stable over time, days working, 40 watts. These high frequency components, very, very difficult to identify the components, is the key point. 5 minutes, okay, sure. This is the key. We need this kind of regime. So more or less as at the minimum of the Pascal curve. In this study, we in this theater, at the room temperature, we studied the pressure needed in our case to have a Pascal regime, and at the local thermometer increased the temperature when it started maximum of the absorption. So correlation, completely correlation. When the pressure was too low, nothing happened. So we are confident that we don't make mistake. In this experiment, the wire temperature was about 700 degrees in power 80 watt, and we get excess heat stable, or about 11 watt, until we change little bit the parameters to check about resistance. So we have the loading of the wires and the chassis heat decreased, but still active, 80 watts, so more than 10%. So it's very, very critical. The window of operating is very, very narrow. And it is the best result, mixture of argon and deuterium. The argon is the lower voltage for Pascal regime, so it makes effect. The pressure just 30 millibar, and we get about 14 watt stable. These are the results about anomalous voltage. In each conference we show data more or less similar, so the effect is reproducible. Still now we don't really understood what is going on anyway. It's very, very reproducible. Anybody can do. Conclusion. The point is, to get anomalous heat, it is very, very difficult. We think we need artificial intelligence to follow the maximum of the system and calibrate voltage and pressure. So my brain now is a bit tired to follow the maximum. In perspective, now computer has the cost very low. Other easy point to increase the voltage from 1,200 to 3,000, 4,000. We have a larger regime where we can work. Maybe increasing voltage more easy, more cheaper than artificial intelligence and software. Some possible explanation why we don't have decreasing of performance. One is flux that we think at the beginning. Another, in our regime, we have like a cold plasma. The cold plasma means the surface of material always catalytic. They don't die young forever. And then we think we have both effect. In the next step, we will use again a special geometry to increase non-equilibrium condition. And putting all together, we think I finish. Maybe will be the event when the cold fusion, will be practical, is not too far from the time. Thanks.
Yeah, I have a question about the temperature dependence. So in some reports last year, it was claimed that there is exponential dependence of the excess heat on temperature. Did you measure anything similar?
Yeah. Yes, I agree. So because exponential dependence, we think it's due to electron component. For the Pascal curve, it's no strong dependence about temperature. But because both works, so, and we need electrons, so the exponential components is okay. We confirm the data.
It's nice to see the constant progression and ideas in your work, Francesco. Just very simply, are you saying that every day of the week you can achieve 14% excess heat? Are you saying that every single time you can achieve 14% excess heat?
Okay. If we give excitation from the beginning, from room temperature, always keep there, the material is active. If we give the excitation when it is high temperature, the system has a lower performance. So means the state of surface, the catalytic properties are key parameter. In people that make sputtering know very well this point. I was surprised I am not sputtering people. Say, okay, it's normal. Why so strange? Oh, okay, thank you. Confirmation. Yes.
I have a personal message to pass on you. If anybody wants to replicate Francesco's experiment, I think there is no problem with you. We can supply an MFMP as available replica cells of Celani. So if you want to try, you can try it at almost no cost. We ship you the cell, you have the wire from Celani, and you can try it out by yourself.
Okay. This is one of the core. This is one of the core of the reactor that my colleague make very, very patiently. Usually during construction it's broken because tight. That I can show to everybody.
A few years ago, you made experience with hydrogen, pure hydrogen, not
Yes.
deuterium, and now
Okay.
you are
Good,
not only
nice
using
question. The point is, if we work with hydrogen and after move with deuterium, we can have some time where you get nothing, and after start again. So I have a tank of deuterium. I decide to work with the deuterium until the bottle is full. Then come back again, hydrogen. Because I have no time to optimization.